Make sure you guys put in a lot of effort in this unit. That I find that the people who try the hardest really do really well in this unit, and the people who try very little do really bad in this unit, and there's not a lot of in-betweeners. So we're going to hope that we have all people who do really good. I actually find this is a hard unit for most people, but by the end, people know it the best and actually do the best in this unit. So it's all in what you put into this unit. So we're going to start off with investigating the fundamental counting principle. So all of this unit is words. All of next unit is words. All of next unit, well, part of next unit, which is called probability, you have to know how to find perms and coms of the probability of perms and coms, sorry. So if you can't do perms and coms, then that section of probability is really hard because you can't do it. It's like a little add-on. So we need to know this really well. So for this one, Lucy is shopping for a sports utility vehicle, an SUV. The dealer says that he has 3 different models and that each model is available in 5 different colors. So let's do a tree diagram for it. Nicely enough, I filled in most of it. So 3 different models. So when you do tree diagrams, for all of you guys who do a tree diagram on a test and then you're going to do it wrong and then you won't be able to finish it, you put the first part here, second part here, and then the full outcome. So people want to write model here and then color down here. No, you write model here and then list all your different models. So the different models are Cross 4, X Ground, and Trail Pro. Then the color off of each model. So off the first model, every single model could come in the color blue, red, silver, white, or black. So I do Cross 4 and it could come in blue, it could come in red, silver, white, black. The X Ground could come in blue, red, silver, white, black, and the Trail Pro could come in blue, red, silver, white, black. So when you do tree diagrams like this, you'll basically have every single outcome listed after. So we have the model and we have the color. Then we have our outcomes. So we have a Cross 4 in blue, a Cross 4 in red, a Cross 4 in silver, a Cross 4 in white, Cross 4 in black, an X Ground in blue, an X Ground in red, an X Ground in silver, an X Ground in white, an X Ground in black. Then we have a Trail Pro in blue, a Trail Pro in red, a Trail Pro in silver, a Trail Pro in white, and a Trail Pro in black. So how many different options does she have? If we add them all up, 15. Lucy has 15 choices. So the benefit of a tree diagram is that every outcome is listed. So you actually see what every outcome is, right? The downfall is if there's 18 makes and each make has 10 colors, oh my goodness, you need a really large piece of paper to draw every single one out, right? So there's got to be a better way, called the fundamental counting principle. So look at the number of choices there are for the model. So how many choices are there for the model? 3. And then how many choices were there for the color? What can we do to these to get our answer? Multiply. The fundamental counting principle states that if there's parts that form a whole, so for example, later on we'll be doing an example about a robot, and the head can be like this, and the body can be like this, and the feet can be like this. So the 3 parts of that robot make up a whole, right? If you have more than one part that makes up a whole, you can take the options of each part and multiply them out and get the total number of options. That's basically the understanding version of the fundamental counting principle. So let's look at C. The dealer tells Lucy that each of the sports utility vehicles comes in 2 editions, standard edition or LE edition. So if we went back and did this on the tree diagram, we'd actually go after this and say model, color, and then we'd have edition. And we have 2 editions. So off each color, you'd have SELE, 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 and you'd keep going, right? Using the fundamental counting principle, it's just another part that makes a whole, right? So the whole car. We have a model, a vehicle, there's 3 of them. We have the color of vehicle, there's 5 options. Then what is our additions? How many additions are there? 2. All 3 of these parts make up the different options that each car has, right? So each car, you can pick the model, you can pick the color, you can pick the addition. So all 3 of those parts make up the one car, right? So then you take those parts, you multiply them together, and you get 30 options. Okay? And flip over. So here is just a little definition of the fundamental counting principle. Consider a task made up of several stages. So like that one was, we could pick a model, and then we could pick the color of the car, and we could pick the addition of the car, right? So different stages. The fundamental counting principle states that if the number of choices for the first stage is A, the number of choices for the second stage is B, number of choices for the third stage is C, then you can multiply them all up. Now, the key is that for that car, I needed to pick one from each stage, right? So if you had like an option of color and model and then the addition, it would either, if you didn't have to pick an addition for each vehicle, then you wouldn't be able to use the fundamental counting principle. But because every task is needed in order to pick that one vehicle, you can multiply them all together. Each different stage, you had to pick something out of in order to make that vehicle. So we're going to look at this example. A toy manufacturer makes wooden toys in 3 parts. Part 1 is the top part of it. It may be colored red or blue. Now, can we have a toy that can't have that top part? No, we have to pick either red or blue. We have to. That's first stage. The second stage, part 2, the middle part must be orange, white, or black. Okay? We have to pick a stage of the middle part of the toy. You can't just get the top and bottom part of the toy. It's not the toy. Okay? And then the third, it can be yellow or green. How many different toys do we have? Well, we're going to make a tree diagram. Just because you can be asked to look at a tree diagram or which tree diagram is correct, you could be asked that. So we need to be able to do a tree diagram. So part 1 we're going to do first. Part 1. The options for part 1 were red or blue. I have those 2 options. Okay? Then I have part 2 will come next. And tree diagrams, most of the time when you've seen them when you did like lowest common denominator ones or GCDs, you would go like this, tree diagrams down. So I feel like everyone feels like they need to go down. Our tree diagrams always go across, okay? So don't try and make them go down. That's the biggest error that happens I see all the time. The middle part can be orange, white, or black. So off of each of these, option 1, I'm going to have 3 options themselves. And I'm giving them space because I'm going to have to go options off of those ones. So orange, white, black. Orange, white, black. Then I have part 3, which is the bottom part. So now if the top part was red and the middle part was orange, I still would have the option of yellow or green for the bottom part, right? If it was red and white, then I'd still have the option of yellow or green for the bottom part. Red or white, I'd still have the option of yellow or green, or red and black, sorry. Blue and orange, yellow and green. Blue and white, yellow or green. Blue and black, yellow or green. So I could list all of my separate outcomes. The red top, the orange middle, the yellow bottom. The red top, the orange middle, the green bottom. The red top, the white middle, the yellow bottom. The red top, the white middle, the green bottom. And I could list all the outcomes out. Or how many are there total? 1, 2, 3, 4, 5, 6. And this one has 6 too. So how many total? 12. So we can make 12 toys. Like I said, the benefit to a tree diagram is that you can see every single outcome, what the actual outcomes would all be. If I use the fundamental counting principle, I'm going to make the parts to whole. So part 1 has how many options? Red or blue? So 2. Part 2 has orange, white, or black, so 3. And then part 3 has yellow or green, so 2. And what do we always do with these numbers when it's the parts to make a whole? Multiply. Now this is another thing to note. If we need part 1 and part 2 and part 3, you multiply. If you only need part 1 or part 2 or part 3, which means each of the separate parts would get you a toy, which it doesn't, you'd add. So if you can use the word and, you will multiply. Very important. If you can use the word or, you're going to add. And that's how you're going to know throughout this entire unit and the next unit whether you're going to add or multiply based on the words multiply or and or. And add, people want to put together because they kind of sound the same. They don't go together. And add do not go together. I know there's 3 letters and they start with an A, they end with a D, and you think, hey, they should go together. They don't. Okay, so think about that. They don't go together. Add goes with or, and goes with multiply. So we need part 1 and part 2 and part 3 to make the toy, so we multiply, which gives us 12 toys. And that's why the fundamental counting principle works. You need each of those parts to make the whole. You need each stage to get the whole thing. Here it is again. In the previous example, the toys of part 1 and part 2 and part 3, the total number of possible toys was found by multiplication. In any example involving and, the total number of arrangements will be found by multiplying. If it's or, you would add them. Yep.
Yeah, that's what.
Yeah. Okay. Here we have a math quiz. Math quizzes consist of questions, correct? Very rarely are teachers nice enough to say you can complete 4 of the 6. You're usually doing this one and 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 this one, and all 6 questions make up the whole test, right? Each question would be a different part of the test. So let's see if we can use the fundamental counting principle on tests. You can, because it's each part makes up the whole test, right? So a math quiz consists of 6 multiple choice questions. That's supposed to be underlined and not lined through. Sorry. My thing is a little off. That's underlined, not crossed out. Okay, so the math quiz consists of 6 multiple choice questions. Those are the separate parts that make the whole test, right? So we're going to put them at 1. Oops, I don't know why I put a comma. I'm used to sequencing the series in grade 11. 1, 2, 3, 4, 5, 6 parts that make a whole. Each of those is questions. So I have number 1, question number 2, question number 3, question number 4, question number 5, question number 6. Okay? Each question has 4 choices. A, B, C, or D. So just like the last toy question, the top part of the toy had 2 options. The middle part of the toy had 3 options. The bottom part of the toy had 2 options. Same thing here. How many options does this number 1 question have? 4. A, B, C, or D. How many does number 2 have? 4. 4, 4, 4, 4. The only way it wouldn't be 4 is if they said if the first question had to be A and the second question couldn't be the same as the first, what would be your options? Then you couldn't use 4, 4, 4, 4 because you wouldn't be able to have them. But that's restrictions which we're going to do tomorrow. So do I have question 1 and 2 and 3 and 4 and 5 and 6 that make up the test, or question 1 or 2 or 3 or 4 or 5 or 6 make up the test? Or and? And if you use or, you're saying I could do question 1 or 2 or 3 or 4 or 5 or 6 for the test. There's not often do teachers let you have the option of doing 1 or 2 or maybe 6 of them, whatever you want to do. So it's and. You have to do this one and 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 this one. So we can write it as 4 times 4 times 4 times 4 times 4 times 4. But often on the test it's written as 4 to the exponent 6. Now people mess this up and they put 6 to the exponent 4. Remember that 4 to the exponent 6 means 4 6 times, right? 6 to the exponent 4 means 6 4 times, which is not the case. So don't get them mixed up, okay? 4 to the exponent 6, someone put in their calculator and tell me what it is. 4 to the exponent 6. It's a large number. Thank you. 4,096. So if you thought, hey, you know, a 4-question quiz, I have a pretty good chance of doing good on it. Just the answer key of a 6-question ABCD test has 4,096 options. Because you could go A for the first one, then B. People have tried this. Don't try and list out all the possibilities, you guys. It's 4,096 possible. You're probably going to miss 1 or 2, or 1,000 of them. Because it'd be like A, then this one could be A. Then this could be A, B, A. Then it could be A, C, A, then A, D, A, then A. Oh no, now it's going to be B, A. You're going to mess one up, right? You're not going to list all of the outcomes. Please don't be that person who's like, I'm never going to learn the fundamental accounts principle. I'm just going to do a tree diagram, and life will be, you will have a tree diagram with ending with 4,096 branches at the very end, like you'd have. The first one would have 4 branches, but then off of each of those 4 branches, you'd have 4 branches. Then off those, it's exponentially growing fast. That is not good. Please don't do a tree diagram. Just fundamental accounting principle. Okay? And some people say, well, will you make me do a tree diagram for this question? Really? I am not that mean. That's mean. Like maybe 2 multiple choice questions, okay. But once I get past like 4, that is nasty. So, no. Okay. Next page. So now we're going to do a little bit of restrictions with the fundamental accounting principle, and then we're going to do restrictions with perms and coms later. So what does a restriction mean? A restriction just means that at some point I'm restricting you to something. So like the last question, I could have restricted you to the first multiple choice answer can only be A, and then the second one can't be. Okay? So that's when you're restricting something. So let's look here. When solving problems involving restrictions, it's important to do the restriction first. Do the restriction first. The restriction is dealt with first. Very important. You deal with the restrictions, and then you do the rest. Okay. So Eric has been assigned the task of determining how many odd 4-digit numbers there are. He has been told the number such as 5267 is a 4-digit number, whereas 0267 is classified as a 3-digit. Here's the key thing here, you guys. Whenever you read 4-digit number, that is a fancy way for them saying that the first digit can't be 0. First number can't be 0. The first number can't be 0. Why? Because if I say I'm going to pay you in, this is really weird, no one would ever say this to you, but I'm going to pay you this month in a 4-digit number, okay? And I'm going to pay you $0,001. You'd be like, no, you're not. That is $1. That is 1 digit. That is the crappiest pay ever. That's what you'd say. Say, okay. I'm still going to pay you in a 4-digit number. I'm going to pay you $0,324. You're like, that's $324, Lepp. That is not 4 digits. That is not good. Okay, I'll pay you $4,567. You're like, now that is a 4-digit number. So please don't be the person who tells me 4-digit numbers start with a 0, because if you were paid as a 4-digit number, you would not want to start with a 0. That would be a 3-digit number. That would be substantially less money. So don't tell me it's 4. Okay? Okay. So you say to yourself, why would they be so mean and not just say how many odd 4-digit numbers there are when the first digit can't be a 0? I don't know why, but they don't. They do not tell you that. So when you see a 4-digit number, you need to say to yourself, that means the first blank cannot be a 0. Okay? Secondly, I ask you, how can you tell me that something is an odd number? No one usually can explain to me how they can tell something is an odd number, because it's just odd. It is. Okay. If it doesn't end in something that's divisible by 2, it's an odd number. Meaning what?
Well, if it ends in like, if it's like 4,758, it's 8.
Yes.
It can be divided by 2.
Mm-hmm.
But if it ends in 4,567, then it's not divided by 2 at the end, so it's odd.
So we're talking about just the end number, right? So I could give you 8 numbers and then the back number. The back number is the only number that tells you something's odd, right? If I say 21, you will all say odd. If I will say 24, you will all say even. If I say 27, you all say odd. If I say 26, you all say even. And then I say, what tells you it's odd or even? You're like, I don't know. It just is. So I didn't change the 2 the whole way along. I didn't change the 2. The only number I changed was the back number and asked you if it was odd or even, right? So the only way that the only number that has to be restricted in order for it to be odd is the back number. And that back digit has to be odd. If the back digit is odd, you can't divide by 2. If the back digit is even, you can. So if you want an even number, the back number needs to be even. The last digit needs to be even. If you want an odd number, the last digit has to be odd. So that's the first thing we're going to do. Now, I showed it in a 4-step. I like doing it in just one line, just so you don't get confused later. But it'll show the 4 steps as we go along. So I'm going to deal with my restrictions first. My first restriction that I'm going to deal with is the back number needs to be odd, right? Because it says it has to be an odd number. That's the only way I can guarantee it to be odd. So I always write my options below and then the number of options above. That's what I do, so it's easier. So also people will tell me, well, 11 is an odd number, so I can put an 11 here. This little blank, oh great, this little blank is a 1-digit blank, so it can only hold a 1-digit number. 11 is a 2-digit number. That would take up 2 blanks, so we can't count 11, okay? So for this back blank, I have the option of 1. I could put a 1 in that blank, or I could put a 3 in that blank, or I could put a 5, or a 7, or a 9. I can't put an 11 because an 11 has 2 digits. It would take up 2 blanks, okay? So how many options is that? 5. And so I put the number of options above. I have 5 options. Now, am I using all 5 of them? No, it only has spot for 1 number, but that's fine. Above the blank is always the number of options you have. So we have 5 options for that back blank. Now, it doesn't say anything about the numbers not being able to be repeated. So unless it says that the numbers can't be repeated, you assume they can. They're not going to say the numbers can be repeated. The only way that you're going to know they can be repeated is that they don't say they can't be repeated, okay? So that means that I could have technically 1, 1, 1, 1, and it would still be the same number. If it said it can't repeat, I couldn't have 1, 1, 1, 1. I could only have 1 once or something like that. So that's my first restriction, is that it needs to be odd. My second restriction is that the first digit can't be a 0, right? I told you that. So the first number can have the option not 0, but 1, 2, 3, 4, 5, 6, 7, 8, 9. How many options is that? 9. Please don't be the person who doesn't count them and then puts like 8 or 10 or something. That is like the biggest like killer on tests, is that people put the wrong, like they'll write the numbers down here and then just put the wrong amount up top. It makes you very sad when you get your test back. Are there any restrictions on the middle blanks? No. So then we can have the numbers 0 to 9 in these middle blanks. 0 to 9 are the only options I have when I have no restrictions, because I can't go less than 0. And I can't go above 9 because then it's a 10-digit number or a 2-digit number, and it would take up 2 blanks, right? So it fills with digit numbers. 0 to 9, common error, people put 9 options. 0 to 9 is not 9 options. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 to 9 is 10 options, not 9. That happens all the time. People tell me it's 9 options. It's not. And then this one would have 0 to 9 again. So 10 options. Now we ask ourselves, do we need this number and this number and this number and this number to make the 4-digit number? Or do we need this number or this number or this number or this number to make the 4-digit number? You need and, right? You need this digit and. So we multiply, and that's why we always multiply. So this is 4,500. So there are actually 4,500 numbers, 4,500 four-digit odd numbers in the world. Now here's the change. B. Eric has now been assigned the task of determining how many odd four-digit numbers, same thing, that have no repeating digits. So now we can't repeat. Okay? So let's watch. 1, 2, 3, 4. So we still have the same options. 1, 3, 5, 7, 9 for the back, right? We still do our restrictions first. So I have 5 options. Then what I do is pretend to keep one of them there. So I'm going to pretend that I put a 7 in that blank. Could I put a 3? Could I put a 5? Could I put a 1 or a 9? Yes. But I'm going to pretend that I kept the 7. Why am I going to pretend that I kept the 7? Because now the 7 is there. That's not an option anymore, right? I kept it there. I can't repeat. So for the first blank, I can't have a 0, right? That was my one restriction. I can have 1, 2, 3, 4, 5, 6. Can't have 7. I kept it there. 8 and 9. Because I'm not allowed to repeat. What if I would have pretended to keep the 1 there? Then I would have listed everything but 1, right? What if I pretended to keep the 9 there? I would list all of them but 9, okay? So there's no like set that you have to keep the 7. I just picked the 7. So how many options do I have? 8 only. Because I'm not allowed to repeat. Now, what one do we want to pretend we keep here now? Pick one. Which number do you want to pick to keep there? 6. Okay. We're pretending we keep 6 here. So that's not crossed out once again. Everyone does usually really good to this point. And then they mess up in the next step. Because what do? They write the leftover ones. Okay, so I have 1, and I have 2, and I have 3, and I have 4, and I have 5, and I have 8, and I have 9. But you forgot that we didn't ever use 0. Because we didn't have the option of 0 back here. 0 would make it even. We didn't have the option of 0 here because we can't start with a 0. It would be a 3-digit number. So you have to remember to include the 0 back in over here. So we actually have 8 options again. Now I'm going to pretend to keep the 2. So now I have 1, 3, 4, 5, 8, 9, 0. So I have 7 left. What's 8 times 8 times 7 times 5? Mm-hmm.
Why don't you know how this is 5?
Mm-hmm.
Why don't we just keep 5?
This is 5 options, not the number 5. So these are the options down here, and the top is the number of options. So yeah, that's the thing that people get confused with when we first start. This is 1, 2, 3, 4, 5 options. So I put the 5 up here because it's the number of options, not actually the 5. We're not keeping the actual 5 there. That's so common. And then here it's 1, 2, 3, 4, 5, 6, 7 options. So I put the 7 up there. I'm not actually holding a 7 there. The only numbers I'm holding are the ones I circled down here. These are the options, the different options. These are how many there actually are. Because if so, this wouldn't be allowed because they're repeated, right? Okay, car number plates in an African country consist of a letter other than I or O. You need to know that there's 26 letters in the alphabet. Nothing worse than someone thinking there's 27 or 21 or something random because you're going to get it wrong. So there's 26 letters. If you have to count them with your fingers, go right ahead. I don't really care. I would rather you do that than write 25. Okay, you have to count them initially with your hands. Seriously, I would rather you get 26 than 25 or 24 because you're too good for your hand counting. Okay, all right. So letters, so it consists of a letter other than I or O. So what I do is I put a blank, and when it's like ridiculous, like 26 letters, I don't go A, B, C, D, E, F, G, H, leave out the I, J, K, L, M, N, O, leave out the O, P, like they're, that would be listing crazy, right? So what I do is I just go, it can't have I and it can't have O. So when it's like huge amount, like once you're listing 24 under the blank, it's starting to get a little crazy. Maybe there's a better way of writing it. Okay? So consists of a letter other than I or O, very important, and I'm going to probably go through it, followed by 3 digits, So 1, 2, 3 digits. 3 digits means 3 numbers. 3 digits. The first can't be a 0. So you can either go 0 with a slash, or you can go 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you can go 0 with a slash. So the first number can't be a 0, and the other 2 have whatever. There's no restrictions on them. Followed by any 2 letters which are not repeated. Followed by any 2 letters. So any 2 letters can be here, but they both just can't repeat. So you can't have like DD or CC. It doesn't say anything about them not repeating with the first letter. It just says that these 2 can't repeat each other. Okay? All right. So we do restrictions first. So the first blank can't have these 2 letters. How many letters are there in the alphabet? 26. So how many are left? 24. This one has how many options? 9. Okay? The back 2 numbers, no, back 2 letters can't repeat. So that's what I'm going to do next. I'm going to do these 2 in the middle last because they're the things without restrictions, and I always do without restrictions last. Okay? So this has how many options of letters? It's A to Z, right? So 26. Now I'm going to pretend that I keep Z there because I don't feel like keeping a different one because it's the one that's listed. So now I have A to Y, which is 25. Now the 2 middle ones can be any digits because there's no restrictions on them. So what numbers do I have when I don't have any restriction on my digits? 0, 2.
100 real quick. Sorry. 126 is A to what?
That's a Z.
Okay.
But yeah. So how many options do I have for when I don't have any restrictions on digits? 0, 2, what number? Rhymes with fine. Thank you. Yes, 9. 0 to 9. You can't use 10. 10 is a 2-digit number. Each blank can only hold 1 letter or 1 number, right? So my options are 0 to 9, not 0 to 10. 10 would take up 2 blanks, and I can't have it take up 2 blanks. Okay? Because 10 would be 1 and a 0. It would take up 2 blanks. So I only single-digit numbers are 0 to 9, which is 10 options. Now people are like, you said 10 can't go in there, and now you put a 10. The number 10 is not an option in here, but this number up here is the amount of options. Okay? So 0 to 9 is 10 options. So I can put 10 options up here. Can I physically put the number 10 in that position? No, but I can put 10 options up there. This is the number of options in these blanks. So this is 0 to 9 again. So I have 10 options. So technically, what could this look like? If I wanted to give a pretend example, A, because it just can't be I-O, 3. This is just an example. 1, 1. A again I could do because it didn't matter. These 2 can't repeat, right? Just the back ones. And then this can't be A. So C. So that could be a pretend option of this number plate. Kind of funny. A311AC. You could find that in the African country of whatever, and its number plate could be that option. Okay? So yes, I have 10 options up here, but the number 10 is not in that blank. Does that make sense? That's where I lose people right at the beginning of fundamental confidence. So how many is this? What's 24 times that?
14,040,000.
So just a few options.
Small.
Now, the Alberta license plates have some restrictions on them too. I don't remember what they are, but there's distinctly like some certain letters can't be in certain spots and numbers or whatever. But let's pretend there isn't any restrictions on them. So we're letter, 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 number, number, number. And let's pretend that there actually isn't any restrictions. I know there's a couple of restrictions, but I can't remember what they are. But let's say that there isn't any. This would be 26, 26, 26, 10, 10, 10, right? Because this is letter, 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 number, number, number. That is 17,576,000. We actually had to add, I think it's another letter, right? I think it's like BBF something. Is it another letter, or another number? Some of them we have number, letter, and I can't remember if they added another letter or number, the new license plates. You gotta have a new one. Number? No, there's 7. No, there's 7. Then that's just someone with a special license plate. Yeah, vanity plate. But there's 7, and I think it's a number. I think it is. I think it's 3 letters, 4 numbers. Anyways, they were worried that they were running out of license plates, so they had to add an extra one. If there happened to have been no restrictions there's 17,576,000. So but if they added an extra 10 to it, that would be times by 10. So then it would be 170 million, right? You just add another 0. That's a substantially larger amount by just adding another digit to it. If you added another letter to it, you'd even have more options because there's times by 26 instead of 10, right? Okay. So this pathway question throws people off, but this totally uses the fundamental accounting principle. So here we have, there are 2 routes from Pitland to Queensland, 3 routes from Queensville, I don't know, I'm reading, Queensville to St. Luke's, and then 3 routes from Pitland to Rutherford, and 1 from Rutherford to St. Luke's. Okay? We can use the fundamental accounting principle on separate parts, because how many paths do I have from P to Q? 2. And how many do I have from Q to S? 3. Now, do I need to take this path and this path to get to S, or this path or this path to get to S? Can you just take this path and miraculously end up in S? Or take this path and just skip these ones? No. You have to take this path and this path to get to S, right? And means multiply. So that's why we use the fundamental accounting principle. So it's 6. So there's 6 different ways. And if you blank, draw them. 1, 2, 3, 4, 5, 6. If you peter out and you're like, I don't know what multiply or add, I don't know, just count them, okay? Now, P to R, there's 3. R to S, there's only 1 option. 3 times 1 is 3. Now, most people can get to this point and then they're like, oh, crud. Do I add the 6 and the 3, or do I multiply the 6 and the 3? So I get a 50-50 guess, and then that's never good. You don't want a 50-50. See if it makes sense. Okay, I have 6 paths here and 3 paths here. Do I take these 6 paths or these 6 paths to get to S? Or do I take these 6 paths and these 3 paths to get to S? Keep in mind, if you're saying and, you're taking every single path to get to S. That is the crappiest way to get to S ever. Like, I got to S, ha, jokes. I'm going to go that, oh, jokes, I'm still not there because I have to go 18 more paths till I can get there because that's fun. No, you don't do that. It's or. So you add them. You're going to take these paths or these paths to get to it. So it's 9, not 18. Keep in mind, if you multiply those 2 numbers, you're saying that you're taking every single path. You yourself, in your vehicle, have to take every single path to get to S. That is bad news bears. I don't even know how you're getting back to P, because you're not to P, but to P. Yeah, get it? Huh? Yeah, nothing. You guys are like death. Just quiet death. All right. I know, fun, right? Sam's just like, oh, we're good.
We did this in the 30 minutes.
I know.
Before I dropped down, and let me tell you, I'm still confused.
Oh, that's not good. Okay. The telephone numbers allocated to subscribers in a rural area consisting of one of the following. So these are your options. The digit 345. So the digit 345, that is the only option. Yeah, so I'll write it like this. This gets a little bit more option. 3 is the first digit. 4 is the next digit. 5. That is the only options. It has to be the digit 345. Just like 403 is how we have to, then our numbers can follow it. 403. This has to be 345. That's their like little area code, let's pretend. Followed by any 3 further digits. So I can have any 3 further digits. If there's no restrictions on those digits, what can they be? 0 to 9. How many options do I have for this first blank? 1, it's the number 3. How many options do I have for this blank? 1, it's the number 4. This one? 1. This one? So I go 1 times 1 times 1 times 10 times 10 times 10, which is 1,000. So I have 1,000 options first. Then it uses the word or. When I read the word or, what should you always think? Add. So I'm going to add these because it has the word or. Now this is my next option, the digit 2. 2. Followed by one of the digits 1 to 5. So I have the options 1 to 5. Followed by any 3 further digits. They can be anything. 0 to 9, 0 to 9, 0 to 9. So one option, 1 to 5 is 5 options, 0 to 9 is 10, 10, 10. 1 times 5 times 10 times 10 times 10 is 5,000. So in total, 6,000 options. I'm going to have you work on some of the questions out of the workbook, and then we're going to finish the rest tomorrow. The textbook doesn't have as good of options, so I like the workbook. So out of the workbook, you guys, for today, if you don't finish, you'll have a little bit of time to work on it tomorrow anyways, because you don't have to take it with you. Page 68. Numbers 1 to 8. Now, can you listen for 1 second? This one gets everyone all the time. So it says, number 4 says this. The score at the end of the second period of a hockey game is Flames 6, Oilers 3. Jerome was attempting to determine how many different possibilities there are for the score at the end of the first period. He used the fundamental counting principle, and he said multiply 6 by 3 to get 18, but he's wrong. So Calgary had 6, and Edmonton had 3. So he said 6 times 3, and he said it's 18, and he's wrong. Now, people are like, but it's 6 and 3. It's 18. It's good. But what do you forget? You want to figure out what's the score could possibly been at the end of the first period. So basically, they could have ended up with this at the end of this is at the end of the second. So the end of the first, they could have ended with 6 and 3, or they could have had 6 and 2, or they could have had 6 and 1, or they could have had 6 and, or 6 and 0. Game start at what? 0, 0. So these options here are actually the numbers 0 to 6 and 0 to 3. So what are we going to actually multiply? 7 times 4. Everyone forgets that the game starts at 0, 0. You don't just it's like start with a score of 1, 1. Like, yay, you both get a goal, right? Not getting a goal, but you're going to get a goal anyways because we want 1, 1. No, you start off with I have nothing, you have nothing, okay? So the options could have been 0 and 6, or 0 and 5, or 0 and 4, 0, 3, 0, 2, 0, 1, 0, 0, or the other way, right? So that question number 4, people get messed up because they forget 0, 0. It's very easy to forget that, okay? So grab a workbook, and you're going to do questions 1 to 8, page 68.